It shouldn't be unmuted. Hold on.
Hi, can you guys hear me online now?
Sorry about that.
Yeah, thank you. Okay. I did an introduction. I'm from SXS, not ETK. That was about all you missed. So yeah, for the first day, Deborah gave a nice introduction to waveforms and how numerical relativity waveforms are used in data analysis for LIGO and searching for gravitational waves in the data. But I want to go over a bit about how we actually extract those numerical relativity waveforms from our simulation. And so the typical method that we currently use to extract gravitational waveforms is a method called extrapolation. And the basic idea behind this is that you have your two black holes and two compact objects orbiting in the middle. You have your outer boundary of your computational domain, which I'll refer to a lot as the Cauchy evolution, the binary black hole evolution. And then inside your computational domain, you have these things called world tubes. And if you remember from GR class, in a space-time diagram, you have a world line of a specific particle through space-time. A world tube is just a collection of particles, and if you can imagine, it kind of makes like a tube as you go through space. And so what you do is you take psi4 at these different world tube radii that are successfully going outwards, and then you extrapolate them effectively with a 1/r fallout all the way out to infinity. And this is how all waveforms are extracted from numerical relativity. Currently, our group does this. Every other group does this. There are a couple drawbacks to this method of extracting gravitational waves. One of them being that you're extracting at spatial infinity, not future null infinity. And we know gravitational waves travel at the speed of light, so they don't actually reach spatial infinity, they reach future null infinity. So in reality, we would want our gravitational waves extracted at future null infinity. In addition, because of this, you won't get a gravitational wave memory, which is a permanent offset of test particles from their original location. That cannot be captured with the shotfish. Also, you don't get any of the other wild scalars necessarily. You might have to do a lot of extra work to get it, but you don't get that necessarily. And then also, it's extrapolation. It's not like you're evolving your space-time out to future null infinity. You're just taking a couple data points from inside your evolution and extrapolating all the way out. And so there can be some inherent error with this in that method. An alternative method for extracting gravitational waves is doing a Cauchy characteristic evolution. And you'll notice here that it says evolution. I sometimes say extraction. We use both, but here I have evolution because what it is it is an evolution of your space-time all the way out to the future. And so going through this diagram, you have your Cauchy domain, which is your typical black hole simulation, and it goes out to some finite coordinate radius. You then have your characteristic domain, which instead of being sliced with spatial hypersurfaces, you now have null hypersurfaces, and they go all the way out to future null infinity. And then in between these two, where they conjoin, what is this world? And so you basically have a separate evolution in the characteristic domain where you have an inner boundary, and the boundary condition supplied on this inner boundary comes from your Cauchy domain. And then that data is evolved all the way out to future null infinity, and it's evolved forward. And so then when you do this evolution, you can get your gravitational wave at. And so I want to first just show the metric that is in general used for Cauchy characteristic extraction, specifically the characteristic evolution part. And so you write your metric in terms of the Bondi-Sachs metric. And the reason that you do this is because it has asymptotically, this will, when it falls off towards a flat Minkowski metric at infinity, you can specify fall off of some of these variables in this metric. I'm not going to go through necessarily these variables and what they mean. U is your kind of time coordinate, R radial, and then X A and X B are your angular coordinates. So this also has your metric. And so when you're going through all this stuff, when you start in your Cauchy domain, you're usually working in your own coordinate system that you did a Cauchy evolution. And it's whatever is good for your own evolution. We specifically use the generalized harmonic formulation with the depth harmonic gauge, but the SSN and moving punctures is a different one that we may do. But then CCE is a completely different coordinate system. So how do we get between the two? Well, we have to implement this quite extensive, complicated list of coordinate transformations to go through. And so you start off with your Cauchy coordinates up here, whatever your simulation is done. Then there's this intermediate frame, which is then sliced on a null hypersurface. And then you get into these Bondi coordinates. And so this is coordinates that I referred to in the slide before with the metric. And you don't stay in these coordinates specifically because these have a pretty strict requirement on the asymptotic behavior of these quantities, meaning that they fall off with something to the flat metric. And we found that in order to evolve things so that specifically one specific quantity asymptotic to the function of Minkowski, you can relax some of the other conditions so that they don't asymptotically fall off to zero, but they fall off to some constant value. And so CCE, the characteristic part, is actually evolved in these partially flat Bondi-like coordinates, not necessarily the Bondi coordinates. And when you think about the evolution, is every time step of your Cauchy, you have data on the world tube, so you have to do this coordinate transformation for every single time step of the characteristic evolution to get the boundary. And so these are the simplified evolution equations for the characteristic part. And this y variable represents your compactified radial coordinate, because we obviously can't extend our domain all the way out to infinity, so we just compactify it into an interval like 0 to 1, minus 1 to 1, something like that. I don't remember specifically. And so you'll notice with a lot of these equations that they have derivatives in terms of the radial coordinate, but there's only one down here that has a derivative in terms of your time coordinate necessary. And so what this means is you only have one evolved variable in your characteristic evolution, and that is this variable Bondi J. The rest of your equations are just constraint equations that you solve on your null slice. And so basically the method that you go through is you have J on a slice, you solve all these constraint equations for the different Bondi variables like beta, Q, U, W, H, basically an alphabet soup. And then you're able to extract you're able to solve for all of your quantities out of functional infinity because you're domain step. Then you just take a time step and do it again. So then what does CCE give you at the end of the day at functional infinity? It basically gives you all of the bioscalars, all 5 of them, the strain and the news. And then it can also give you the retarded time that we have out there. And these are what you need to do basically waveform analysis. Psi4 and the strain are very important for gravitational waves. Psi0 is incoming radiation, so not as important. Yeah. And so before I go into kind of explaining how to get the CCE module, how to run it and everything, I wanted to make a note about hydrodynamics, GRMHT, because I know a lot of people here do hydrodynamics and are maybe wanting to extract gravitational waves from binary neutron star simulations, stuff like this. And so what I'll say is that if your world tube that you are extracting your metric data at from the Cauchy evolution is in an area where there's only atmosphere, then this works pretty well. And the reason is because the metric that I showed you above and the CC evolution is only done in vacuum. There's no matter taken into account for that. The stress energy tensor TU is set to 0. If you extract your gravitational wave, or if you have your world tube in a region of space-time where there is a lot of matter with self-gravitation, we're not really sure what happens. Haven't really tried it at all. So it's kind of up in the air. It could be okay. It could also not be okay. We're not sure. But as long as your worldview radius is an atmosphere, we're pretty confident that you'll get out a reasonable gravitational wave that you can use for analysis. Also, this image was not produced by SpECTRE, it's produced by SpEC, but this is what Francois could give me at last the short minute notes. Okay, so now going about obtaining the CCE module and using it. Basically, everything I'm about to say from now on is on our website. We have this CCE tutorial page right here from the main page of our website. So if you ever have questions or are confused about what I'm saying here, you can just go and look right there. And then we're also available on GitHub, so you can ask us. So obtaining the CCE module specifically, one way that you could do this is from source, where you can download SpECTRE, download all of its dependencies, build it, and then run it. But I would not personally recommend that. I have done it on many systems, and it is terrible, in my opinion. We have so many dependencies that would just make this almost impossible for somebody just starting out. And so if you really want to try it out, you can, but I would not recommend it. Instead, we do releases every month, and starting from the one that was just released yesterday, we are going to be offering, if you click on the release and go all the way bottom down here to the assets, we are offering a tarball. It has has the CC executable and some other things in there that will allow you to run everything. This executable is statically linked. You only need a couple very low-level libraries on any system to run it. So you can just download this tarball extract and then run system. Inside the tarball specifically, we have the characteristic extract executable in green here. We have a .yaml, which is our input file format. We use YAML instead, and so this is an example input file that you can use that all the defaults are effectively set to what you would want to do for a run. We have world2 data, which is this Bondi SOX R200, means it's extracted at our coordinate radius 200. And then this other H5 file, the underscore expected, this is output running this example world2 data through the CCE executable, and then you should be able to get the same thing out. Then we have a little Python script here that will check that you specifically got the same thing to make sure it's working at first. And then I will come back to the reduce world2 executable in a second, which is separate. And so where can you run this? We've tested this currently on Expanse, Anvil, Stampede 3, Delta with you have to set the environment variable first, Perlmutter, and then any Ubuntu distribution 18.0 or later. Those run natively on the system that we've checked. We also offer a Docker container that has a full SpECTRE environment in there. And then we are able to run the CC executable through the Docker container using on a cluster like Apptainer or Singularity or something like this on Frontera and Delta. Frontera just particularly has the old libraries there, and we don't know why. So we basically decided not to support Frontera natively because it's so how to run CCE specifically? It's a pretty simple command. You just execute characteristic extract, give it your input file, and that's it. Now, if you're running in the container rather than natively, all you have to do is add a little thing before that just says run through Apptainer. You have to download the dev Docker image first, and then just Apptainer exec the Docker image while running this command, and it'll run on your system. So now for the world2 data. And so I think this is probably the most important part for people outside of the SXS collaboration, because you need to get your data into our world2 format so that CCE can read it and use it. And CCE currently supports two different formats for the world2 data. The first I'll be talking about is a Cartesian metric format. This is basically your spatial metric, your lapse, your shift, and then the time and radial derivatives of all of those components. So that's quite a bit of data. All of this data, though, is represented in terms of spherical harmonic coefficients, like is necessary even for extrapolation. But like I said, this is a lot of data to dump to disk for every time slice. And you have to dump it pretty often, especially near mergers, so that you can get a good resolution, temporal resolution to runs. And so Deborah will actually be talking about this in a little bit for the ETK side of getting the simulation data into this format. The other kind of format that we have is Bondi socks. And so this is basically the alphabet soup of Bondi variables that I was talking about before. H, J, U, R, U, W. I don't necessarily know what they all mean. They're in a paper somewhere. I can look them up. They're also represented in spherical harmonics, same way, but because you're storing a lot less components than the spatial metric, which you have 10 labs, 3 for the shift, and then also their time and radial derivatives, it's about 4 times more space efficient to store on disk. And so we actually had to do this because Zenoda was pretty unhappy that we were storing too much World 2 data on their servers. So we had to decrease it a bit. And so this, that executable that I was talking about before, the reduced CCE World 2 will actually take metric data in the Cartesian metric format, and it will just convert it to the Bondi socks format. And so this way, if you want to dump, if you don't have the transformations to be able to put your data into the Bondi socks format, you can just dump it in the Cartesian format and then convert it to Bondi socks. I think eventually I want to be able to support reading in maybe just instead of dumping it as spherical harmonics, just dumping data onto collocation points on a sphere and then just having CCE do the transformation itself, but that's probably longer. We'll see what that happens. And so I wanted to just give an example of what the World Tube data looks like from a simulation. I was thinking about showing the Bondi socks format, but I didn't think that would be super helpful because a lot of other people work with lapse shift and space-time metric. And so we decided to dump the lapse from one of our simulations and see what that looks like. And so keep in mind that this is for a generalized harmonic evolution system with a damped harmonic gauge system. And so we don't evolve the lapse, just kind of, you can calculate it though. And so this is what the lapse radial derivative and time derivative look like. Kind of oscillatory specifically for the imaginary part of the T2 mode and extracted at about 300 M. I think more important than what is useful as a check for what your data looks like is plotting the amplitude of all of your modes and seeing how they decay. Because as you go to a higher and higher mode number, meaning higher L and then consequently higher M, you should basically get this kind of decay off to machine precision at the very top. Because the modes L equals 2, L equals 3, L equals 4, those should be the dominant ones in your simulation. And then everything else should be basically subdominant. So this is a pretty good sanity check, I think, that your extraction is going correctly, more or less. And so we now have in our differential equation solver, we have boundary data for this inner boundary up here, the World 2. We don't need to apply boundary conditions at future infinity. We do need to supply initial data for the initial time space. And so, like I said before, we only have to specify Bondi J because that's the only evolved variable, and everything else can be just solved from radial derivatives and ODEs. And so there are, this is, I want to say, a very active area of research because it is not necessarily known what the best way to do this is. We have ways currently right now, but they definitely can be improved. And so the current ways that we have right now, one is called conformal J. And what this means is that you take the take your Bondi J variable at your one point down here, your initial World 2 point. You do a conformal transformation and such that different one of the Bondi variables, beta, falls off with a specific, it falls off in a specific way. This is our recommended way to initialize, get initial data for the null slice. I will say that if something is going weird in your World 2 data, the conformal factor can get pretty large and blow up, and then this will cause that coordinate transformation of going from your evolution coordinates to the Bondi coordinates to the Bondi-like coordinates. The Jacobians of that can become ill-defined, so then you actually can't do that. You can't initialize your hyperspace. So additionally, we have a second recommended, which is just inverse cubic. And what this is just you have a 1/r and 1/r cubed. term, each of them with coefficients, and you match these coefficients such that it matches to your world 2 boundary here, and then it falls off. And the advantage of this method is that it's really robust. I don't think we've ever had a simulation where we use this kind of initial data fail. It's very robust. But the downside of it is that there's a lot of junk radiation because it's not necessarily initialized in the best way. And so with conformal J method, there is less CCE junk, which is going to be pretty important. Later on, I'll show you. Inverse cubic there is, and there's a couple other methods that we have, but they're further down on the priority list. And so now we're going to look at some just raw CCE output, the things that you get in the H5 files right after the simulation runs. First, we're going to look at the imaginary part of the 2-2 component of the strain, and you'll see that it does some wiggles, like you expect a waveform to do, which is pretty good. But the longer that you look at this, you might notice something strange going on there. You might notice that the oscillations aren't really centered around 0. And then at the very end, your waveform doesn't die off to 0 after the black hole's finished. What's going on? You can see this a bit better if you look at the amplitude of the 2-2 component of the strain. Ideally, what you would expect is just a smooth line that goes up and then falls back down all the way to 0. We don't see that here. We see a bunch of oscillations. Then we also don't get back. And so you might think that there's a bug in CCE. So far, we don't know of any, but there's always a possibility. But there's an explanation. And this is because the frame that your CCE output is in is not, quote unquote, correct. It's not physical. So you have to perform a method called frame fixing in order to get your waveform into a more physical. And so we know that GR is covariant, and this basically says that you have no preferred frame for doing anything. But as we know from all of our Cauchy evolutions and our binary black hole simulations, there are some that are more useful than others, even if there's no preferred. And so at SpECTRE, if you think of things in terms of group theory, you can represent things in terms of the bonding methods in their SOX group, the NFs and symmetries, which is an extension of the Poincare group. And so you can do any of these transformations that those two groups allow you to do. And so there is a frame that some of my other collaborators have found that you can transform your metric into that is a much more physical frame than the one that CCE initially outputs in. And this is called the super vessel. And there are a couple of transformations that you can do to get into the super rest frame, the most important of them being a super translation, which is effectively a angularly dependent time translation of your waveform. And the reason that you can do this is because at future null infinity, you are effectively causally disconnected from any other observer. And so you're free to time translate your coordinates however you want. If you were not at future null infinity, if you're at some finite radius, you'd be able to send signals to each other to coordinate all your clocks and you'd be able to synchronize. But at future null infinity, you're not able to do this. And so the super rest frame is particularly important because it is necessary to basically do all analyses with a CCE waveform. You have to get your waveform to a physically motivated frame so that you can do analyses such as quasi-normal mode analyses, or just comparing waveforms to other groups. If you remember, your Cauchy evolution is in different coordinates than somebody else's, and so when you go through that huge transformation of coordinates to get to the Bondi-like coordinate, they're still not necessarily going to be in the same frame. So if you want to compare waveforms across groups, you need to have a common frame, and this is the rest frame. And then also being able to do convergence tests. And so we're not just going to leave you high and dry and say, you need to do this without giving you the tools to be able to do this. And so there's a GitHub repo maintained by Mike Boyle, a collaborator in SXS, called SpECTRE, which will do all these transformations for you. And so if we go back to the imaginary part of the 2-2 component of the strain, and we now run the CCE output through the frame fixing code SpECTRE, you can see that waveform now is oscillating about 0, and then falls off to 0 at the very end. And so this is a confident way we can see that we are in the correct super rest. And this is even more apparent if you look at the amplitude again. So this is the one from the raw output from CCE. But then if you look at SPECTRE, you can see this very nice smooth increase of the amplitude all the way to merger, and then falls back down all the way to 0 at the end of the axis. But you also may notice there's still some oscillations here at the very beginning. And this is the junk, the CCE junk radiation that I was talking about before. And this is highly dependent on the initial data that you use for J on your initial process. And so you'll notice that this analysis was run with the conformal J initial data, the better one that we have. And you still have junk radiation all the way up to 1500 M. And so effectively, to be able to use this in waveform analyses, you have to cut off the first 1500 M of your simulation in order to use the nice smooth part. This is why the initial data for J is still in active area research, because we really want to try to reduce this as much as possible so we don't have to throw away so much of our waveform. And then I also mentioned memory before, so I can't not show a talk about gravitational wave memory. And so this is the memory stored in the 2-0 component, the real part of the 2-0 component of the strain. And so this is the raw CCE output, and you can see that it goes up and then it goes down back to 0. But remember, this is not, you cannot trust these results really. You have to frame fix before you actually interpret any of your results. So this is, once you do frame fixing, you still exhibit the same behavior, and you have this constant offset after the black holes merge to have gravitation. And so frame fixing is particularly important because naively, when I first saw this, when I looked at the 2-2 component of the strain, and I saw that there was this offset from CCE, I was like, oh, that's gravitational wave memory. It's a persistent offset of your space-time. But that wasn't it. That was just because you were in the wrong super rest frame. This actually is gravitational wave. And so that basically wraps up my little tutorial part of CCE. On the left here, I have a QR code that you can scan, which will take you to the our website with the CCE tutorial, and it will go through all of this, also link you to SpECTRE and everything, and show you how to, and it goes into a bit more data about the world tube data format and the output and all this kind of stuff. And then over here on the right is a QR code for the SpECTRE repo, which is also linked in our tutorial, but I just thought I'd throw these up here to show you. And then up next, Deborah is going to be talking about, just right now, about how to get ETK data into the world tube data format to read into SpECTRE. So let me stop sharing my screen. Deborah can come up here.
Deborah gets set up. Let's thank our first speaker here.
Thanks guys for having me again. Sorry that you have to hear me talk so much, but this one will be short, I promise. All right, so I just want to talk a little bit about some work that I've been doing on the ETK side, collaborating with Nora Gadiri, who's also here, and Professor Helgi, about how we can use SpECTRE CCE module using Einstein toolkit simulations. I want to highlight that this is still work in progress, so don't judge things too harshly. All right. So just a quick introduction to our motivation, though I think Kyle already gave most of this. CCE in general is more accurate than doing analytic extrapolation. And you can also use it to directly obtain all the Weyl scalars as well as the news and the strain, which is also nice because typically in Einstein toolkit simulations, we just get psi4 natively and then usually do the Fourier transform trick to get the strain. But going from psi4 to strain, we lose things like the memory effect. And so that is another benefit of being able to do CCE. Now, other people have already pursued CCE in Einstein toolkit. You may have heard of the pit null code and its associated thorns. But for this project, we're particularly interested in using SpECTRE CCE code so that we can do cross-code comparisons with the various CCE methods as well as between Einstein toolkit and spec simulations. So that's what I'm going to talk about today. All right, so what does SpECTRE need us to give it? Well, the metric and gauge information in ADN variables, including the lapse and the shift, which are what define how you move between your spatial slices, as well as all the 6 independent components of the metric, and the radial derivative for each of those, and the time derivatives for each of those on finite radius spheres decomposed using the spherical harmonics. So that's what my goal is to output. All right, so Einstein Toolkit Thorn coming soon. It's not there yet, but one day soon, hopefully this summer, we will have a Thorn design that outputs the metric, lapse, and shift data, as well as their derivatives, in a format that is already parsed and shaped to just directly feed into SpECTRE CCE so that you don't have to do any additional post-processing. What the user will specify in their parameter file is just the radii at which they would like to do the extraction, how frequently they want that in terms of iterations, the number of theta and phi points to use on the sphere, so we'll make that optional and have some defaults, and the maximum L value for what your spherical decomposition should go out to. Okay, so just brief overview of the methodology of how it'll do this is we're using the ADN-based grid variables for the lapse, as well as its time derivative, and the shift, as well as its time derivative, and the metric and the extrinsic curvature. It's worth noting that the time derivative of the metric is not directly stored as a grid variable, but the extrinsic curvature is, and you can compute the time derivative of the metric directly from the extrinsic curvature, the lapse, and the shift. And then once we have all of those variables, we use the carbon interpolator to interpolate all of these quantities onto the user-specified radii. And also you can use the interpolator directly to compute the radial derivatives. Then we integrate over it to compute the spherical harmonic decomposition and export it in the SpECTRE format, which is in changes fastest order of columns in an H5 data set for each variable. All right, so what is fed into CCE? So yeah, once you've dumped all of this using the Thorn, you'll have some data that looks like this. This is to try to match what Kyle showed. And so here you've got the real component of the 2-2 mode of the lapse, as well as the real component of the lapse for all of the different modes that I output for the this is just the index of the in varies fastest format. You can see a similar decay as you saw with his. It was worth noting if you're looking at this and thinking mine doesn't look the same, mine only went up to 160. He had like 600 modes. So that's why you'll notice a different shape there. All right, great. But now what we're really interested in is the waveforms that come out of the CCE. So this is for a non-spinning equal mass simulation, relatively short, with just separation at 8M. And this is the 2-2 component of Psi4, the real part. And you'll see 2 different extraction radii here. We've got 70M and 90M, and then the waveform output from CCE. In the future, I would like to output more of these radii, particularly some further out, so that we can really see this extrapolation and how it would go if you did the analytic extrapolation. But at least with this preliminary work, you can see kind of, it's hard probably from there, but it's moving in the right direction, and it seems consistent with what we would expect the extrapolated waveform to look like. All right, so just wrap up with what's still left to do on this, which is a decent bit, but check with the larger extraction radius, larger grid, or resolved grid, hopefully longer separation as well. I showed you the Psi4 because the strain looked strange, because I think the frame fixing. And so that's one thing that I want to do. And then I also want to compare with the pit null CCE results. We already have that available, and then we can do a direct comparison essentially between the SpECTRE one and the pit null one. And then unfortunately right now I have to do a little bit of post-processing to get it quite into the SpECTRE format, but by the time I release this Thorn, that won't be the case. And then hopefully publish it in an Einstein Toolkit release, maybe November. We'll see. All right, that's it. Thank you.
So Are there any questions for either Kyle or Deborah?
Looks like lots.
Let's start with Zach. Okay.
Yeah, so this question could go to either of you. Both showed a very similar plot of collapse and LM modes. So it looks like a lot of these, if I'm understanding this correct, which I might not be, can you go back to say slide 6?
I can show you.
There we go. So I'm trying to understand the right plot there. So this is the real part of the LM.
Oh, shoot, I actually made a mistake.
Ah.
That's not the real component. It's real and imaginary going back and forth. Because the real component's in one index or one column, and then the imaginary is next.
Okay, so it's something like up to the L equals 8 mode? I don't know.
L equals 8.
L equals 8. Okay, because, okay, so it goes up there, okay, because, yeah. L goes from right side plus. Perfect, okay. All right, so it looks like only a very small fraction of them are significant. And this sort of goes into my next question. That is, how much data do you have to store? There are a few very related questions. How much data do you have to store? How many radii are useful to output these on? And then finally, is it a good idea to just truncate the modes if they're below a certain power? That's part of that. So sorry. Go ahead.
Deborah, can you, for the benefit of online, can you repeat like a quick summary of the last part of that question?
Yeah, so Zach was just talking about the plot on the right of this screen and about how only a handful of the modes are particularly significant or significant at all, and then asked a few questions involving how many radii are useful to export to, how much data you need, and whether it be worth truncating modes so that, I assume, so that you don't have to store as much data. Okay, so to address some of that, I mean, it depends on how much you want. I mean, in theory, I would think just having one radius, essentially, that's good, should be fine for doing this. I had a couple so that I could do some comparisons. Then I had a couple more so that I could do some sanity checks on my radial derivatives. But I think if you're wanting to compare it with other extrapolation methods, you might need more. But essentially, it should all work fine with just one. Something else I would like to do, actually, though, that's a good question for, is try outputting on multiple different spheres, feed it into the SpECTRE CCE, and then compare the output, make sure that that's all same. So that would be my answer for that. I will note that for this simulation, I was only extracting at radii of like 90 was my highest because I was using a really small grid to get this done. But I think the documentation for SpECTRE says preferably do at least 150. So something worth noting on that. Okay. And then, yeah, I mean, the lapse is pretty uniform on the sphere. And so it's not a surprise that most of the other modes aren't particularly dominant. But I mean, I agree, all these at 10 to the -17 seem kind of like a waste to be having to store data for. But I don't know if that's something you guys would consider not to feed in.
Yeah, so
5 minutes.
starting out. Yeah, for this plot, it is the amplitude of just
What? No, this is on the right?
Yeah.
No, because that's the whole thing is these are.
Oh, yeah, the amplitude of launch. Yeah. Okay, so for how much data you need in terms of time, I think we dump stuff a certain fraction of an orbit every time because that's the temporal resolution you need to resolve the gravitational wave. So I forget what that fraction, but some fraction of an orbit. We do dump several extraction radii, and the reason for this is because it's not really guaranteed that one radii is better than the other for all simulations, and so we actually dump a range between 100 and like 300, 350 or whatever, and then we'll run CCE over all of these different world tubes and just take the one that's the best.
Can I ask a follow-up question? Best to find how?
That is a great question that I probably am not the person to answer, but this is how it's described. Let's keep it at that. I'll check it out. In terms of the amount of data here, so we usually usually dump at around L equals 16 on the world tube. And the reason that you do this is because when we dump the data for at SCRI, the final output, we only use like an L of 8. And so if your world tube data on the surface is not sufficiently high, you can get mode A really sync. Based on the truncation of that regional. So yeah, about double is about what we want to observe at regional infinity versus the world tube itself. But yeah, a lot of them are pretty close.
But my question is, how many gigabytes is that
Oh.
HDF file?
Gigabyte.
Is it many gigabytes? Is it a terabyte?
It's not nowhere near a terabyte, but it's probably a couple gigs. Yeah, for a full for one of our waveforms, which is like 20 orbits, 2,000 amps, like that.
Yeah, I don't think mine hit a gig, but it was a small simulation. So.
More questions? All right, it's on the right there.
Okay, so the question is about slide 7. I'm just wondering, in what sense is the waveform extracted at low be more accurate than just extracting it at a finite radius?
Well, it would be more accurate in terms of what we see as observers when we detect a gravitational wave from a binary black hole super far away. We are not at 70 GeV or 90 GeV. That thing has been traveling for a really, really long time, a really, really far distance away. So it's not necessarily that these aren't accurate, but they're not accurate for what we see. Also, the fact that the gravitational waves are really defined in the weak field regime, and that's a little ill-defined when you're close. I think I mentioned that. Where is your accuracy? Or that depends on you.
So is the CCE jump that you mentioned, any way related to actual jump every day?
Oh, from the Cauchy, from the
Can you repeat Peter's question?
Peter's asking about the CCE jump, whether it's related to the CCE Bell slice initial data or the Cauchy initial data.
Well, the actual initial data on the based on.
Like is
Which
the-
space-time simulation?
But what the initial data of your.
that's taken-
There are two of those. Yeah, there's the Cauchy one.
The ones you start with basic underlying space.
Oh yeah, the Cauchy one. We found that for our Cauchy evolutions, that the jump radiation from that is fairly high frequency around the when you extract it out gravitational waves, and it doesn't last this long. The CCE jump is from the initial null slice data specifically, and it's a lot lower frequency and it lasts longer. So it's not as much from the Cauchy evolutions as it is from the characteristic. Yes, John was asking about the SpRI module in Python and if you have to do anything else to be able to extract the waveforms or if you have to rerun CC. What I know, if you want to, I personally have not used SpRI that much. In order to just make the plots that I was showing, you just need to roughly know the total ADM mass of your system. And it's assumed to be 1 in a lot of our simulations, which I think TK does as well. And then you just have a time array that you can interpolate to, because we do dump a lot of, world, do times, and CC does output a lot of times depending on the time step of CC. And so you can interpolate to a less dense time array, reduce the amount of data that's grabbed. But other than that, no, you just CC. No, the super rest frame is also referred to as the center of mass frame. So it puts it into the center of mass frame.
Roland, and then I'll jump back.
So actually two questions. First to Kyle, I guess. So that's what I thought. I think there was already a prior project where people tried to look at how CCE works in spec and try to compare that from the simulation. I think one of the things that was found there was that the two evolution systems behave very differently as far as how sensitive the gauge that you're using. That's still the case, or has there been better understanding exactly what one has to do to get a good diffraction radius?
Yeah, Roland's asking about the gauge necessary for CC, and if work has been done since the implementation of spec. I think yes, some people have worked on it. I think that was part of Jordan's work when he ported the implementation from spec to SpECTRE, is he did a lot of work for the coordinate transformations of the gauge to make it more. I don't know if it's stable to that right, but yes, work has been done. I'd have to get back to you on specifically what was being done and everything. Yeah, sorry, I don't have a better answer for you for that.
We got a chat question, so let me jump to that. Chat question is, the way you would use this is one, to run a cactus simulation and output a file, or two, run CCE to find a waveform at I+. I'm actually not sure I understand that question, but the
Does
first
it mean
part
run
is,
it concurrently, like run the characteristic evolution concurrently with an Einstein toolkit evolution?
Steve is not, that's not a question. Okay, but those are the two steps apparently, it's Steve's.
Okay, so is that just a clarifying question? Like, is this what we're thinking? Because if so, yeah, the idea is run it through Cactus. Cactus will output the file that would be ready to be run through CPE, and then run it through CPE to get it at my point.
Afterwards, in kind of a post-processing step.
Back to that.
Two questions.
You get one, and then we're going back to Roland for his second question.
Do you write that apps one?
Apparently not. Oh, because I switched.
Is there something special? Like, I guess, why are those levels so much higher than the rest?
Just this shape. So he asked if there's something special about those modes that are particularly higher than the others. Well, the main thing I would say is just that the lapse is a pretty at R90. It's just pretty uniform on the sphere. Not exactly. There's some deviations. If it were perfectly uniform, this would be essentially the only mode that would have anything. And it's just close to uniform. And so you get clearly some other stuff. But here, for example, it's the 2-2, or this is the 0-0. But yeah, it's just that it's the shape of the spherical harmonics and the shape that the lapse tends to take. So pretty uniform with these other modes being interesting. Why the other modes, these specific modes are the interesting ones, I don't know off the top of my head. Someone else might. I think that'll be something that'll be pretty standard across all simulations using the same gauge.
Roland, your second question.
That's a good question for Deborah.
Okay.
In your cactus code that extracts the data for SpECTRE CCE code, this is all operating on ADM based variables that will work with any evolution code, and I forgot, you need just that chip also time to use those.
Right, so he asked in my cactus implementation of this, if I'm using the ADM variable so that in theory it should work with any evolution code, and what exactly are the variables that I'm needing. Yeah, so in theory, it's working right now with just the ADM based stuff. And so as if other evolution codes are writing back to it, then it works with any evolution code. right now, I'm also, so yes, you need the labs, the shift, and their derivatives, which some of the other codes don't write back to. Fortunately, right now I was using Lachlan VSSN, and it does write back to it, it seems. But you could compute the time derivative from your time series data, but then you're adding an extra error and stuff by doing
And in the back, the same question.
So I'm assuming the reason you get the straight correctly is all the way out.
Yes, the reason you can get the strain directly is because you're evolving answers. Yeah, you evolve the metric all the way out to digital infinity.
Okay, and then so, out of curiosity, guys, if you compare that waveform, with straight directly versus like it's integrated, what it's like forward. Are the template.
Yeah. So he asked about the comparison of once you do it's similar to this plot, but for strain, if you do it with the CCE versus if you're doing it with strain where you've done the FFT. And I wish I had that plot for you. I was hoping to show that plot, but unfortunately, I think I'm having issues with the frame fixing, and so the comparison was, well, awful and meaningless because my strain just went like this when I did the CCE. But have you guys done any comparisons with if you compute strain from bipolar? I don't know why you guys.
I think, well, our whole catalog is using extrapolation right now, so I think they have done some
Right,
comparisons.
but you guys directly get strain from the simulations, whereas we get bipolar. So you don't tend to do the FFT.
Yeah.
Kind of integration.
I don't know if anybody has.
That's definitely a comparison we will do once we get this. For the, okay.
I think.
Hmm.
Here, side four, that you get a calculate with the same like stuff.
Okay.
And we found that this is much better than advantages. The advantages that struck very very close to the what we don't have. So much. But we've never found that in particular what is that we actually found. And I'm surprised. It's so random. What's the best one? Like,
Yeah, the world tubes. It's never the smallest one. It's never the largest one. It's often the second smallest one that we do, like around 150, but it's not always, which is why we run multiple.
Okay, last question.
Okay, maybe it's a question for,
You're good.
So when you evolve your fiber surface, what kind of boundary conditions do you impose?
The only boundary condition you have is the inner boundary at the world tube, and that's supplied by the calcium.
Okay, so you don't put anything.
No, because there's nothing coming in from future null infinity.
Okay.
There's nothing outside of future null infinity coming in.
So the characteristic one is not opposed. But we kind of bypass that situation by unicorns parallelogram algorithm that basically steps. It's like, you know, what I mean, I'm building my step while I'm working on it. So in this way, you step on the first characteristic, so you put more or less a better boundary condition. So I don't think the spectral methods. This is fine.
Yeah, I think one thing that I think a student might be trying to implement now is maybe similar to that is to get more data points on the initial null slice to be able to initialize it better, you need multiple Cauchy slices that at multiple world tube radii. And so I think somebody's gonna be looking into that this summer / fall. It's a student project that's gonna.
Okay, let's thank both our speakers again.